Okay, so here's a solution to exam 3. There are 3 different versions of it, so I'm not sure exactly which one this is, but all the solutions are basically the same. It's just different values. I'll post the values in a different place. Okay, so in this first problem, we have this L-shaped piece, A, B, C, which is rigid. You can see that it's all connected as one piece. And it's connected to this actuator, which is traveling with a known velocity and acceleration at point A. And we know what the angular velocity and the angular acceleration is. The dimensions are provided down here. So this is 10 inches, this is 4 inches, and this angle is 35 degrees. The angular velocity is positive. That means this is counterclockwise at 4.5 radians per second, although its direction won't matter. We'll see here in a second. Its angular acceleration is 7, and that is also positive, therefore it is counterclockwise. And the velocity is positive. That means it's going upwards at 6 inches per second, and it is slowing down, therefore, because its acceleration is negative, so it's in the negative direction. And we want to determine the acceleration vector in terms of unit vectors for point C at the instant using vector math. I think the most important aspect of this problem is to have read it correctly, right? And then to look at it and observe that all we're doing here is finding the acceleration of a point, knowing the point. So our main thing that we're trying to find is the acceleration of C with the acceleration of A plus the acceleration of C with respect to A. And we know that this has 2 parts to it. We could also have just gone to our equation sheet right here and taken a look at this guy. A similar thing, although we're C instead of B, and come to this vector relationship. So our first task is really to find all the ingredients that we need for that. You could make the case that this is a problem that is almost entirely plug and chug, just using vector math. So anyway, I'm writing down the equation that I need right here, but in terms of C instead of B. And let's see, we'll say alpha K cross with R C with respect to A, right, minus omega squared R C with respect to A. These 2 parts are really what that is right there. That's all that's going on here. So I didn't do a very good job with my writing down of the thing. Let me write that a little better. RC with respect to A. All right, so I need to get RC with respect to A, but I'm given this little thing. So there's really the only little snag that we have. So we need to find this length right there. That is going to be RC with respect to A. So the length of RC with respect to A is going to be the square root of 10 squared plus 4 squared. 10 squared, 4 squared plus square root. We get that it's 10.77, and where are these? These are in inches, right? And then we need the angle that's formed right here, right? And maybe I'm going to call that theta AC. I don't know. I just come up with a name, theta AC. So that's the inverse tan of rise over run 4 over 10. Is that right? Yep. And so we get 21.8 degrees. Now we need to know this angle right there. I maybe wanted to call that AC. I don't know. But anyway, I'm going to call it beta. I needed to come up with a name, so beta is just going to be 35 degrees minus 21.80. So we get 13.2 really degrees. Now I need to know this R with respect to RC with respect to A. So we're going to go upwards and to the left. So RC with respect to A is going to be this length 10.77, and it's in the negative x direction because it's to the left, times the cosine of 13.2 I plus R, and we're going upwards, so it's positive 10.77 sine of 13.2, and that'd be J, and these are inches. So we plug those in, I'll do the cosine of that times that, and I'm going to get our C with respect to A is negative 10.49 I plus 10.77, and take 13.2 and take the sine. It's not going to be very much. It ends up being 2.459 J. Now we can, maybe I want to write out, no, I think we're okay here. So C is going to be the acceleration of A, which we know is in the vertical direction, but it's negative, therefore it's negative 10 J plus K, this guy, and he's positive, so he's going to be 7, like I said alpha, 7, crossed with this, so it's going to be negative 10.49, and then K crossed with I, and then plus 7 times 2.459 K crossed with J. Go to this, a negative omega 4.5 squared and multiplied by negative 10.49 I plus, whoop, I need to make that negative, whoop, it's still negative, right? We have to distribute that across there, so that's still negative 4.5 squared, 2.459 J. We know K crossed with I is a positive J. K crossed with J is a negative I. You could do schemes, or you could have just memorized that. So now what we need to do is just find what our things are here. Okay, so there's a J, here's an I. We have negative right here. So we take 7 times 2.459, and that's negative. And then this is negative, but that's negative, right? So we have 4.5 squared and 10.49. We're multiplying it by there. I think I did something wrong here. Wait a minute, double check here. 4.5 squared, yes, okay, times 10.49. Yeah, okay, good. So we have 212, but that's positive, so we're going to add them. So we get 195.2, and then I have a negative 10 for my J. I'm going to have 7 times 10.49. Right, and that's also negative, so subtract that out. And then lastly, we have this one, 4.5 squared and 2.459 times, and it too is negative. So we're going to get a negative 133.2. And that right there is the answer. It's a fairly straightforward problem, only having to recognize it just looks maybe like you need to do a lot more to it than you do. I tried to tell you during the exam that we were not to overthink this one. So that took 10 minutes to do. Let me pause, and I want to double check my Excel that I got this right. Okay, good. So I confirmed I had this one right. Number one right. Okay, so we have this crank slider, and we have an angular velocity of looks like -6. So therefore, this must be going clockwise at 6 radians per second. And we have these dimensions. We want to use ICR method to determine the velocity of the piston. Just to note that this was almost identical to a problem that we did in the review session. I just turned it sideways, flipped it around. Okay, so I'm going to redraw. Well, first off, what I want to do is find out the velocity of B. So I'm going to draw part AB by itself, and I said that this was 6 radians per second, right? Therefore, it must be traveling upwards with the velocity of B right there. And the velocity of B is going to be omega AB times L AB, or 6 times 0.4. I think I could do that in my head, but I'm going to do a calculator anyway. 2.4. And these are meters per second. Okay. Now our next task is to find the ICR. So looking up at this, I don't have enough room to really draw it out here, but maybe I'll draw it down here. I have a velocity that I know that direction right there. That is our VB. So our line is going to be along this right here, perpendicular to it, right? We also have this line of action right here, right? Which I'll transfer down here. So it's either coming that way or that way in terms of its velocity. We want to go perpendicular to it right there, and that is going to be our ICR. And let's see, looking at the angles right here, we could say this right here is theta C. So this right here must also be theta C. And my way of thinking of that, this is just my way, is I rotate that, right? See, I rotate this theta C, and we can see that this closes, so these must be the same angles right there. That's my own personal way of doing it. And we'll notice that this is perpendicular. So this right here is going to be RB with respect to ICR, and this right there is going to be RC with respect to ICR. And if this is the ICR right here, and that's the velocity, our omega, we call it BC, is going that way. And therefore, this velocity must be coming that way. So there's going to be our result. It's going to be right here. So now we need to find this RB with respect to ICR. And the geometry is not terribly difficult. I mean, we know that this right here is LBC, that length. So in this case, here's the angle, and here's this. This is going to be the run, and we want to find the rise, right? So we just have to multiply our LBC, which is 0.6, times the tangent, right? Because that's rise over run. We want the rise. We know the run. We just multiply the run by this. And so we get 35, take the tangent, 0.6 times, and we get this is 0.4201 meters. While we're here and doing this, let's get the RC with respect to ICR. Now, this is the hypotenuse, and this is the adjacent, and we want the hypotenuse, so what we want to do is divide the adjacent by the cosine. So we go 0.6 divided by the cosine of 35. 0.6, 35 cosine divided 0.7325 meters. And okay, so now we're armed and dangerous with everything we need. We know the velocity of B. We can find omega BC by taking VB and dividing by the RB with respect to ICR. And that's 2.40 divided by 0.4201. 2.4, and I get 5.713 radians per second. And now I want to find the velocity of C. And so now I take the omega BC times RC with respect to ICR. And I take 5.713 times my 0.7325. And I already have those in my calculator, so I just hit times. And I go 4.184 meters per second. And so my answer is 4.184 meters per second, 35 degrees. And let's see how much time that took. So that was that took about 6 and change, maybe a little 6 minutes. So I'm 16 minutes into the exam, and just double checking. Yeah, I got it right. I'm good. That's good news. All right. So the last problem is an acceleration problem, where I ask you to do the acceleration in. See, I'll hide that. Do the acceleration. Let's see here. Okay, so we have a standard piston problem, and so it's a single cylinder engine, and we have the crankshaft angular velocity right here. I also gave you the connecting rod angular velocity so that you didn't have to do a velocity analysis. The dimensions and parameters are right here. So at this instant, right, well, let's see. Well, first off, this is 12 inches. This is 20 inches. This is 35 degrees. This is 20 degrees. It's actually an approximation. It's actually like 20.1 degrees. But anyway, I didn't make you do that calculation. But based on this angle, this length, and this length, you could find this. So I'm giving you extra information. And then, as I said, this is going to be counterclockwise because it's positive. But this one is clockwise, right? So, yeah, you can kind of see this right here. Right? So this is... I'm thinking of this thing. I think I have that correct. That sounds right. Yeah, that one's moving that way. Yep, that's correct. Okay. So anyway, let's find. We want to use the 3 diagram method to find the acceleration of C. So we have to first find the acceleration of B. So this guy, and he's moving at a constant velocity, right? Omega. So he's got a velocity coming this way, but we don't really even care about the velocity. But this is what AB, right? What we care about is the acceleration here at B. And since it's constant, the only acceleration that this thing is experiencing at this instant is the acceleration of B, with respect to A in the normal direction, right? So it's coming downwards that way. So it's just omega AB squared times L AB. So 7 squared times 12. It's an important thing to just see your way through this, right? So we get 588, and these are inches per second squared, right? Now we're all set for doing the acceleration in the 3 diagram method of this. I'll just try to make this thing look about the same, about right. There you go. So here's my 3 diagrams. And the one we know is going to be down in this direction. All right, and let me see. Let me make sure I get this angle correct. Because I gave you this angle right here as being 35 degrees, this angle right here is 35 degrees. Therefore, this angle is 35 degrees. I'm going to write this. Should I write this? I'm going to write it as acceleration of b. Yeah, there you go. This acceleration has to be in the vertical direction. We don't necessarily know up or down yet. So let's not bother like deciding yet, but we do know that it's 0 in the horizontal direction, which should be a clue from our practice problems and homework and so forth that that's going to be the key to being able to solve this. So we place this acceleration at both locations here. And might as well put the angle right in there, 35 degrees. All right, and now since this is the reference, this is going to be the pivot. And we do know that this thing is going with an omega BC. We know this magnitude. We don't really care about the direction, but we do know that's going to cause an acceleration of c with respect to a in the normal direction, which is going to be omega BC squared times LBC. And while we're at it, let's be a little careful here and remember we know that angle is 20 degrees right in there. Now we have to decide on which way we think the acceleration is going to go. I say the best way to do this is take tangential acceleration, I say, and make that go counterclockwise. So here is my assumed direction, and that's going to be the acceleration of c with respect to a tangentially, which we know is alpha BC LBC. I'm going to go ahead and write out what this numeric value is going to be. I think that makes it easier to do. And so we're going to have 3.661 squared times our 20, and that ends up being 3.661 squared 20 times, so I get that's 268.1 inches per second squared. Maybe I'll actually write this one out too. That's just going to be times 20. And something else I might want to note is that right here is also going to be 20 degrees. All right. So we're all set up. So what the equation we're writing that corresponds with this 3 diagram is the acceleration of c is equal to the acceleration of b plus the acceleration of b with respect to c. But I said c, no, I did that totally wrong, and I wrote that wrong too, and I wrote that wrong. There you go. B, c with respect to b. There you go. Sorry about that. Plus the acceleration of c with respect to b in the normal direction. All right. So the x direction is going to help us because it's going to be 0 right here, and that's going to allow us to get, that's our strategy. So in the x direction, take 0 is equal to, okay, so this is in the negative direction, and it is the acceleration of b, which we found up here, 588.0, but it's going to be the sine of 35 degrees. All right. Then we come over to here, and we see that it's going to be also in the negative direction based on our assumption, alpha BC times 20. But now the cosine of 20 degrees. And then this one is in the positive x direction, and it is 268.1, but the sine of 20 degrees. So you can see that we're going to be able to solve for alpha BC. So let me take sine of 20 and multiply it by my 268. And okay, so this is negative, so it's 588 and 35 sine times, and I'm going to subtract it out. So I get negative on this side right here. So I get a total of negative 245.6. I'm going to bring that on the other side, but I'm going to get a negative here. So I get a negative answer, and I'm divide that other side by 20 and divide by the cosine of 20. And so I get a negative 13.07 radians per second squared. So my guess was wrong, and a lot of times I'll write this underneath and I'll go guess. My guess was wrong, but I'm going to continue with my diagram in my y direction. I'm going to continue with my diagram, but then when I get to the place where I need to put this in, I'll put it as a negative right there. So I'll keep my diagram with my guess. So my acceleration of c, I'm just going to say, just choose as positive right here. And so I'm going to have a negative acceleration of b, which is the 588.0, but only the vertical component, so the cosine of 35 degrees. And then I have a negative here, but I'm going to put what? I said negative. Yeah, it should be negative, right? It should be negative here because this is going downwards, right? That arrow is going downwards, but the arrow is going downwards, but it's actually wrong, so we ended the negative. So there's where I'm accounting for the fact that I made a wrong guess. Is here. Here's the guess. Here is what actually happened. So they're going to count each other out, and I'll get the correct thing. And so I'm going to take it times 20, and now it's going to be the vertical component of it. So that's the sine of 20. And often I could just look up at this one and see that's cosine. That has to be sine. And then this is going in the negative direction down here. So it's negative, and this value, 268.1, but now only the vertical part, so that's the cosine of 20. And if I do all of that, I get my 588 and 35, go to the cosine of that times, right, and make that negative. And then I'm going to take my 13 and 0.07, multiply it by 20, multiply it by the sine of 20. I should assume, and I'm going to add it. So I still have a negative number, so I'm going to get a negative number here because I have this. I have 268.1 and the cosine of 20 times and minus, and I get a negative 644.2. And these are inches per second squared. And I'm a little concerned that I didn't get what I expected out of this. 1 second here. Let me double check everything that I have. All right, so this is down. I'm okay with that. That's why 5. This is like I might have made a mistake up here at the very top. Did I make a mistake? I had 7. Acceleration. Interesting. How did I mess that up? I need 12 and 20 and 7. Okay, wait. 12 and 20 and 7. That's what, for some reason it's not, I messed this other thing up. All right, so I needed 12, 20, 35, 20, and I need a 7 right there. And okay, pause. just wanted to confirm and find out if I made a mistake. It might be my Excel was wrong. So, you know, the answer, I probably could accept the negative right here, but really this should be a vector. So let's say we'll do it this way. Right there would be the technically correct answer. So the exam took 30 minutes to explain. You had 75 minutes. I think it's close to the 2.5 to 1 ratio that I like to have. You know, I expect the students to take 2.5 times what it would take me to do. Sometimes I usually try to do a 2, but I went to go for 2.5. Hopefully, all of this makes sense, and we will make sure you come and discuss it with me if you think there's something unfair.